So this time I'm going to talk about conditioned generation models, and this is the encoder-decoder models that we talked about in the reading. So language models are generative models of text, like I talked about before. So basically you have a probability of X, and you generate a sentence from it, and you can get something like this Harry Potter ish thing here, which doesn't look very much like Harry Potter. So anyway, conditioned language models are basically things that don't generate text. They generate text according to some specification. And the encoder-decoder models that I talked about before are basically a subset of these conditioned generation models. So an encoder-decoder model is something that encodes something into a vector, then generates from it. But you could also think of a conditioned generation model where you don't have the encoder. So like if we have input X, the output Y will be text because it's a language model. But the input can be anything we want. So for example, if we have structured data in a natural language description, so we could go from like basketball scores into a description of a basketball game. If we have English and Japanese, we could go from English to Japanese, or a document to a short description, an utterance to a response to that utterance, or an image to text, speech to a transcript. So all of these correspond to a task in natural language processing. Do we have any guesses for what these are? The first one's actually maybe the hardest. Yeah, it's called natural language generation. So normally when people say language generation, this is what they meant until about a couple years ago, and now a lot of other things are called language generation, probably appropriately. This one's, whoops. That one's translation, so what's the next one? Yeah, summarization and... Yeah, I'd say dialogue response generation, maybe. Yeah, captioning and speech recognition. So all of these are conditional language modeling problems. So before neural nets, these were all treated in very different ways. But now with neural nets, basically, if you know how to create a neural net, you can do any of these. You might not be able to do any of them very well, but you can do any of these to some extent, I guess. So the formulation, we want to calculate in a language model, we would calculate the probability of a sentence like this. So if you remember our language model probabilities, it would be P of the next word given all the previous words, and we multiply them all together to get the probability of X. So yeah, that's our next word in our context. So for conditioned language models, all we do is we say we want to generate a sequence Y. And in addition to all the previous words, we include X as well. So we include our input X as well. So yeah, we add that context. So one type of language model is the recurrent neural network language model. And one type of conditional language model is the encoder-decoder model. So the encoder-decoder model, basically we have our encoder up here and our decoder down here. So that's what was covered. This was mainly what was covered in the reading. So I think this is clear to everyone, hopefully. No questions so far? Okay. So the first thing we need to worry about is we have an encoder and we have a decoder. So how do we take the information calculated from this encoder and pass it on to our decoder? And there's a number of ways we can do that. And these are things we consider in all conditional language models that we make as well. So maybe not necessarily just encoder-decoder models. So the first way that people did it in this paper by Sutskever et al., basically what we do is we take our encoder, and this encoder calculates a hidden state. Then we initialize our encoder, our decoder with that. We can also transform into different dimensions. So let's say we want a decoder that's bigger than our encoder. We can do something like a linear transform, and then if our linear transform is from a vector of size 3 to vector of size 4, then we can pass along things of different sizes between them. Another thing is you can also input at every time step. So the first modern paper on neural MT is this Kalkbrenner neural machine translation, is this Kalkbrenner and Blinson paper. And basically what they did is they took the encoder state and they generated, and they fed it into the decoder every time. So basically it's like a language model, and the language model at every time step can reference the thing that you encoded from the input. And this has connections to attention, which I'll talk about next time. So the encoder-decoder model, despite being kind of a revolution in a way, is extremely simple, so simple that I only need to spend like 3 slides on it. But in terms of a model, it's extremely simple, but the difficulty comes when you want to actually generate things from this. And so in the reading, I talked about different types of generations. So we have a model, P of y given x. So how do we use it to generate? And I guess there's basically 2 methods. One is sampling, and one is kind of argmax. I also talked about n-best argmax in the reading, but these are the 2 that you can. These are basically the 2 that you can do. And for sampling, it's a simple algorithm like this. So while you haven't reached the end of the sentence, you randomly sample a word from this probability. An important thing about this is an exact method for sampling from P of x, or P of y given x. Which means that we don't need to even worry about like a search problem when we're trying to sample. So this is the best possible sampling algorithm we can do. It exactly randomly samples from this distribution. So are there any questions about sampling?
How do you actually sample a word from distribution?
Oh, okay. So I'll give you the complicated answer first, and then I'll give you the easy answer after that. So the way you would do it if you actually needed to implement it is you have a distribution, and you know this distribution adds up to 1. So what you do is you randomly sample a number from between 0 and 1. Let's say you get 0.7. And then you step through this vector, and you subtract the value here. And after you've subtracted the value here, let's say our probability is 0.4, 0.2, 0.3. So every time after you subtract, you get 0.3, then you get 0.1, and then you get minus 0.2. So then the moment you go under 0, that's the index you want to choose, and this will allow you to exactly sample from this distribution. So this is the complicated answer. The simple answer is in Python. There's a, I think it's random choice, or something like that. Is it random choice or choice? Random choice, yeah. So there's a function in Python called np.randomChoice, and you can use this to randomly sample from the Python. Yeah.
For like very large vocabularies, do floating points become an issue?
For very large vocabularies, does floating point precision become an issue? My guess is probably no, and the reason why is because your distribution is going to be pretty peaky most of the time. And when your distribution is very peaky, you have a vanishingly small chance of sampling something with a really low value. When your distribution is very flat, then your floating point precision is actually pretty reasonable, right? Because you're using, even if it's a really large vocabulary, you'll still get some probability on most of the things. So I guess maybe not, but actually I've never quantified it, so that'd be interesting to try. Yeah. Any other questions? So there's actually an example of this in the code sample if you want to look more carefully. So you want to do sampling basically when you, or no, actually I'll talk about greedy search next. So greedy search is exactly like sampling, but one by one you pick the single highest probability word. So you just step through and you pick the next word with the highest probability. And this similarly can be done by np.argmax in Python. And this allows you to pick the word with the highest probability. So basically sampling and greedy search are exactly the same except for which function you call here. So this is not exact, and this causes real problems. So this is something to be aware of when you're implementing things. Greedy search will often generate the easy words first. And also greedy search will often prefer multiple common words to one rare word. So an example of this that I actually found in one of my neural machine translation models was I had a model that wanted to pick between New York and Pittsburgh, for example. And it also had something like New Jersey as an option. So if you have a 0.3 probability of New Jersey, a 0.3 probability of New York, and a 0.4 probability of Pittsburgh, then these two added together will be 0.6. So the probability of new becomes higher than the probability of Pittsburgh. So greedy search picks new, and then after it picks new, it has to pick York or Jersey. So it would make a mistake translating Pittsburgh into New York, which we cannot allow as CMU members. Okay. So this, because of this, you have this suboptimal search problem. So there are a bunch of different ways to fix this, and I will be talking about some. Sorry, go ahead.
What do you mean by exact?
Oh, exact. So what exact would mean is when you try to take the argmax of. Oh yeah, actually, the slides aren't very precise. But if we have the whole sequence. The probability of the whole sequence, we want to find the sequence with the highest probability and return that as our output. And greedy search will not find this sequence with the highest probability. It will find the next word with the highest probability, but it can make mistakes like this one if you look over the whole sequence.
But even random sampling is not exact.
So random sampling will exactly find something distributed according to this. So if you take infinity samples, you will get the exact distribution according to this. So if that's kind of a property of ancestral sampling, and if you don't believe me, you can either look ancestral sampling up on in a course materials or something, or you can implement it and see that it actually finds it.
In that case, is there an inexact sampling method?
Yeah, so there are inexact sampling methods. This is going to turn into a machine learning class if I talk about them, but there are methods where the distribution you want to sample from is not a distribution that you can calculate efficiently. And when the distribution you want to sample from is something that you can't calculate efficiently, sometimes you use a different distribution to sample from. And there are ways to correct for that, like sampling from the distribution, then readjusting. So there are methods like importance sampling and Metropolis Hastings. So those would be two keywords to look up if you're interested in sampling. Okay. So any other questions? No? Okay. I will, so beam search is a very typical way to do this, to fix this problem. Because I'm going to talk about search more in depth later in the course, I'm not going to cover it in a lot of detail. I think many people have seen this before in other classes. But the basic idea is greedy search is keeping your one best the one best word at every time step, and beam search just keeps the k best words, where you set k to be 2 or 5 or some larger value. And this helps prevent search errors. And the larger your k, the fewer search errors you will have usually. Yeah.
So if your k is equal to your vocab size, you'll get the exact solution.
No, that's not the case. Because the number of hypotheses that you get is actually the vocab size times the sequence length. So, it's actually the vocab size times the sequence length, and if there are some interactions between that, you could potentially have problems. So you would have to set your beam to be equal to, sorry, not times the sequence length, the vocab size to the sequence length. So you would have to set your beam this big to be
Isn't
that
that like
solution.
a dynamic programming solution?
So that's a good question. For this model, there is no dynamic programming solution. And that's actually one of the features of encoder-decoder models compared to other models that we used before. So I'm going to talk about conditional random fields later, and conditional random fields have an exact dynamic programming solution. But the reason why encoder-decoder models don't have a dynamic programming solution is because in their recurrent decoder, this state depends on all the words you've seen previously. So that's an exponential number. Yeah.
So for the topic that you mentioned on board about
Uh-huh.
picking words that are high frequency,
Yeah.
can you tell me about some picks that can solve that problem? Like, what kind of methods are adopted to overcome that?
Well, so this is an important difference to be aware of. So there's two types of errors that you can make. One is a model error and one is a search error. So what I'm talking about here is purely search errors. So this is assuming that your model is actually giving the highest probability to something, but your search algorithm is not able to find it appropriately. In this case, beam search is one way to solve that. So you make your beam bigger, you'll get better at searching, and you'll make fewer search errors. If it's a model error where like the frequent word gets a higher score, then there are other ways to fix that, which I'll talk about later. For example, you can penalize things that are frequent, overall, while not penalizing things that are frequent given the context, for example. But that's something I'll talk about at a later time. Okay. Anything else? I think these are all good questions, so I'm happy to answer them. Okay. So I have an encoder-decoder example. I won't go through the code of the model so much because I think you can imagine what it looks like. But just to kind of show the generation process. So the generation process, you basically calculate the representation of the sentence, and then you calculate the representation of the sentence, and then you start the target, and then you iterate through. And at every point, you kind of do an update of your current state by adding the input, getting the output. You calculate your softmax. You calculate the log of the softmax, and then you take the max. You take the max of the probabilities using the np.argmax function, like I suggested, and that gives you the next word. And then if the next word is your end of sentence symbol, you break. You're done. And then you return your target sentence. Otherwise, you add the word to the target sentence. So it's pretty simple. One small note is that you'll notice that I'm iterating over a range from I to maximum sentence size. And the reason why is because when things go really badly in your model will generate infinity tokens, and you'll run out of memory on your GPU, and your program will crash. So it's important to kind of put a hard limit on your sentence size, and usually we do something like 200 or whatever. So yeah, that's the basic idea there. Are there any questions about this? Yeah.
Why do you need to do a softmax? Like, if you're just doing the argmax,
Mm-hmm.
scaling the results wouldn't make a difference.
That's an excellent question, and we don't have to do the softmax in greedy search, but we do have to do it in beam search. Because in beam search, we're actually comparing across multiple time steps, and there the scaling is important. Yeah.
Can you just expand a little bit on the? So I understand like why it's a problem to generate infinite tokens. Why is that memory going to be taken out of the GPU? Shouldn't it be coming out of your RAM in general as opposed to your GPU's RAM?
Well, it depends on. So the question is, why would the memory come out of your GPU? So if you're doing search on your CPU, you could do it on the CPU. Also, if you're kind of clever, you can kind of get rid of the memory that you've already used, and search forever. But either way, you don't want to search. You don't want to search forever. You don't want infinity long sentences. So,
I guess the question then is like how do you even execute the search on the GPU? Because it's a linear. I would think since it's a linear process, you wouldn't.
Oh, so search on the GPU is slow.
Okay.
So very often it will be faster to search on the CPU, unless you have very large like vocabularies or something like that.
Why would the search be slow on the GPU? Aren't they like just tensor operations?
So why would the search be slow on the GPU? I think the main reason is usually we search one sentence at a time, as opposed to during training we do big batches of
Why is
data.
it necessary?
Well, I guess usually you get one sentence at a time. If you're a big web service, you might get multiple sentences at a time. I'll send them to a batched like search
I'm talking
operation.
Just like suppose you're doing machine translation and you have a validation set, you can
Uh-huh.
easily batch the whole thing, right?
Yeah, you could do that. If you batch your validation set, then it would be faster on the GPU. Yes, that's true.
And also, do people use other variants like other than say greedy beam search, something similar to A-star search or something?
Something similar to A-star search. So A-star search is, I think many people are aware of this, but A-star search is basically an alternative to beam search where you have a heuristic function. Yeah, I'm going to talk about this in a later thing, but just there's a paper called Learning to Decode for Future Success, which is not doing A-star search because A-star needs an admissible heuristic and this is an inadmissible heuristic, but the idea of considering the future while you're doing search is something that people have thought about. It just adds a lot of complexity, so I think that the reason why is because of that. Another auxiliary thing is for problems like machine translation where your model is pretty good, actually surprisingly beam search with a small beam does quite well in terms of search, and it's difficult to find too many explicit search errors, even with a beam of like 5. Which is somewhat surprising. So I think that's the reason why people haven't quite focused on search as much as they did.
That's just like on a very benchmark data set which have very common words and stuff like that, right?
So I think people don't actually know the answer, and people, including me, don't actually know the answer. But I've heard that on Dialog, people use larger search spaces. So on Dialog, you have more uncertainty. And therefore having a larger search space is important. But yeah. Okay. Any other questions? Yeah.
So by training this encoder decoder network, so do we feed the actual sequence into what is there in a training, or it's we actually whatever model generates that feed?
So do we feed in the actual sequence, the ground truth sequence? And the answer is traditionally yes, we do. Feed in the ground truth sequence, but I'll be talking about a lot of other methods that don't feed that in. The disadvantage of feeding that in is it becomes very brittle to mistakes. So if you make a mistake, it continues to make mistakes for the rest. But I'll talk about that in a lot of detail in like 2 or 3 classes. So I'll talk about it. Okay. So The next thing that I will talk about is model ensembling. So model ensembling is basically combining together two different models. I talked about it very briefly in the reading material, but I'm going to give a little bit more intuition here. The first thing you should know about ensembling, so yeah, ensembling is combining together the predictions of multiple models. So the reason why we want to combine together multiple models is if you have two different models that were trained in a different way, either because they have different random seeds when you started out training, or you shuffled the data in a different way, or they were trained on different data, or they have different architectures, they tend to make different errors on the output. And because they make different errors, these errors tend to be less correlated than when the models are. And models tend to be more uncertain when they're about to make errors. And because of this, if you have one model that's very uncertain and another model that's very certain about its output, the model that's very certain about its output will basically win here. And because models tend to be more certain when they're correct, this helps, basically smooth over the fact or prevent errors. It smooths over idiosyncrasies of a particular model. And this is one of the most effective things you can do if you want to just raise your accuracy. Ensembling is extremely effective at raising accuracy. And it's so effective that people in papers say, basically ensembling is almost like cheating. So when you compare two models, you shouldn't compare an ensembled model to an unensembled model. You should compare unensembled models to unensembled models. So just be aware that this is very effective. The disadvantage of this is as you increase the number of models you train and use in test time, computation time scales linearly. So if you want to train 3 models, it takes 3 times as long to train the models. Yeah.
So the reading mentions training different models, the same model with different sort of initializations.
Mm-hmm. Yep.
Does it make sense to take completely different models and then ensemble them?
Yes. So in general, I can give a few tips about which models you should put into an ensemble. In general, diversity of the models is good. So models that make different mistakes are good, precisely for this reason. It helps smooth over the idiosyncrasies of the model. So the default thing that people usually do is they do random initialization of the parameters. Another thing you do is shuffle the data differently in different orders. That also adds variance. Another thing is different model architectures. So the model, you might have 2 different options and ensemble them together. So there might be other things, but I think those are the main things you do. And the one thing is that the models should be approximately similar accuracy. So if you have one model that's way worse and you ensemble, that can decrease your accuracy. Yeah.
So how are they trained? Are they trained together? Like all of them, and do they take the average error?
Usually they're trained independently. And the reason why is because you want them to make different errors. So if you train them together, that will correlate their errors.
Okay, so at test time, we just take the most correlated finalized prediction.
So I'll explain exactly how you do this in a second. So let me explain how you do this in an actual model. So what you do is when you calculate the probability, you take the weighted average of m model probabilities. So this is the probability according to model M, and this is the probability of model M. The second term is often set to the uniform distribution, 1 divided by m. So what this means is basically, practically from a neural network standpoint, usually you get a softmax, or you get a probability vector from model 1, and you get a probability vector from model 2. You just add these together, divide by 2, and then make your prediction. So at test time, you have multiple models running kind of in sync, and then when you finally make a prediction of what word to do next using your np.random choice or np.argmax, you do that according to this probability. Yeah.
Is there any scope of trying to learn the second one?
So is there any, has anybody tried to learn the second function? So what that would mean is instead of doing this, you do something like 0.3 and 0.7 or whatever.
Condition on whatever. it is.
Conditioned on things. And yes, there's an excellent paper written by me. There's various papers by various people. I had a paper at NLP 2016 where you learn how to interpolate things together. Long story short, if you have very different models, it usually helps. If you have the same model with random initialization, I actually tried to learn these values once, and it didn't really help at all. And in fact, it learned to basically do the uniform distribution, which made me feel really bad because I'd spent like 2 days implementing this thing, and then it just learned to do the same thing as I was doing before. But I think if you have very different models that are good for different things, then this is useful. Yeah.
Can you use the accuracy such a model when scale them so that they add up to 1 and use them as
Could you use the accuracy of the model and scale them to add up to 1? That would be one way. That would be a kind of heuristic way. I think if you wanted to do this, it'd be better to, kind of come up with a loss function and say this is the loss function I want to optimize, and then I will scale based on that loss function. Yeah. Okay. So there's also log linear interpolation. So the previous one is a linear interpolation of the probabilities where we take the mixture like this. So log linear interpolation looks like this. Basically what we do is instead of taking the probabilities, we take the score before the softmax. And we add these scores together. And then we do the softmax one more time. And this allows us to basically renormalize these scores into a probability distribution. So that's the interpolation coefficient for model M. This could also be something like 1 or 1 divided by M. The log probability, and then we normalize. The interpolation coefficient, again, is often set to the uniform distribution. So the natural question here is, yeah, sorry.
So for the log linear model, you're not learning this during training time. Right? This is just for prediction. You have independent models that you've trained, and now you're trying to predict using this function.
This is just at test time. So actually, any of these could also be used at training time if you wanted to. But
I'm just thinking like the softmax of that thing is probably not easily differentiable. Right? It's going to take a lot of time.
It's going to take just as much time as your normal softmax over your vocabulary because it's the same size. So if you're already calculating that in your model, it actually doesn't make any difference. Yeah. Or not much difference. Okay. So then the natural question here is which one should I use, linear or log linear? And basically, you can think of linear and log linear interpolation as logical operations. So the linear is like a logical OR. The interpolated model will like any choice that any model gives a high probability. So for example, if model 1 gives a probability of 0.4, and model 2 gives a probability of 0.00001, 0.4 is a high probability, so you'll still get a probability of like 0.2, 0.2, etc., which is still reasonably high. On the other hand, so this is good to use in models that capture different traits of the problem. So if you have different models, it's also necessary when you have any model that can assign a 0 probability. And the reason why is because log linear is like a logical AND. The interpolated model only likes choices where all of the models agree. And this is good to use when you want to restrict the types of possible answers. So let me explain this in a little bit more detail. So let's say you have let's say you have a model 2 that basically gives you a probability of 0 over this particular choice. After you take the log, this becomes negative infinity, right? So negative infinity plus anything becomes negative infinity. And because of that, the probability of this becomes 0. On the other hand, in log linear interpolation, on the other hand, in linear interpolation, this would still be 0.2. It's a relatively high value. So if you want to have one model that can say no, never give this output, then log linear interpolation is your good choice. If you want to have like either model be able to contribute probability, then linear interpolation is a good way to go. Any questions about this? Yeah.
To better ground my understanding, can you give me a real example of where a linear model was used or log linear model?
Okay, so a real example where a log linear model would be used is, let's say you have a, let's say in encoder-decoder model, you have some model that basically predicts, overall, by looking at the entire sentence, which words you think are going to appear in the sentence. And it can predict, and what you want that model to do is you want it to restrict your vocabulary so you won't generate anything completely crazy. And in order for it to restrict your vocabulary, you would need to use log linear interpolation, because then that model could say, no, I hate this word, you should never generate this word, and then it will give it a very low probability. It will be ruled out for the rest of the generation, I guess. On the other hand, linear interpolation would be good if you have, let's say you have a language model trained on one domain and a language model trained on another domain. Or you have a big language model trained on one general domain and a small language model trained on your target domain. And you want to do like domain adaptation, basically. In that case, you don't want to have the in-domain data only be able to generate vocabulary that's seen before, so you want either model to be able to propose vocabulary that you'd be generating. So that's when you would want to use linear interpolation. Anything else? Okay. This is kind of a hack. It's not an actual method for ensembling, but it does something that's pretty similar to ensembling. It's parameter averaging. So the problem is that ensembling means we have to use M models at test time. It also means we have to train M times if we have M models in our ensemble. So this increases both training and testing time a whole lot. So what parameter averaging does is basically what you do is you write out the model several times near the end of training, and then you take the average of the model parameters afterwards. So that this means that you train for maybe, let's say you train your model for 20 epochs, and then for the 16th, 17th, 18th, 19th, and 20th epoch, you print out the parameters, and at the very end, you average them all together. So the intuition behind this is because you're training with stochastic gradient descent, you're going to have your loss go down like this, and then at the end, you're going to be like kind of bumping around and having slightly different models at the end that are all approximately good. And then by averaging the parameters together, you can kind of iron out the idiosyncrasies of the model. And this is pretty effective empirically, although I don't think there's a really good theory of why this should be a good idea.
The models would have to have the same architecture for this, right?
Yeah, so this only works within one training run. It actually doesn't work at all across training runs either. And I think you might be able to think about why. Because hidden states, you can randomly permute the hidden states, and you'll still get the same model. And if the hidden states are permuted and you average everything, then things would just break. So it only works within one training.
So you can argue that towards the end of training, you are around the local minimum, so the function is locally convex, so averaging makes more sense.
Yeah, although between training epochs, it's probably not convex, but averaging, because you're in a local minimum and you're not moving that much, averaging will make a lot more sense than if you're going from like this a function like this, and then you average your two minima and get here, then that would be bad. So, yeah.
Like Ensemble, is this considered cheating?
I'd say no. I don't really consider this cheating, and the reason why is because it doesn't increase your training or test time complexity. Although I don't know, it's kind of on the it's on the gray borderline. Yeah.
Can dropout be considered as equivalent to Ensemble?
So dropout is interesting in that it's kind of equivalent to ensembling. What dropout is basically doing is there's a way you can view it as training exponentially many models, where basically the size of the things that you're dropping out is a big binary vector, and you're randomly turning it into 1 and 0, right? And then whenever you have one active, whenever you have the one active, that basically specifies which of your exponentially many models you're using. And then in the end, when you don't do dropout, it's like using all of those models at once. It's not exactly equivalent to ensembling all of them together. In order to ensemble all of them together, what you would have to do is you would have to actually expand all of those exponentially many models and use all of them and ensemble them together. But it's pretty close, I guess. So, yeah, there's a strong connection between them. Anything else? Okay, I will move on. So another thing that's kind of interesting is ensemble distillation. So the idea behind this is that the big disadvantage of ensembling gives you huge accuracy gains. So it's very useful, but the problem is at test time when you want to actually deploy the system, you get this huge ensemble of models with tons of parameters, tons of calculation time. So what knowledge distillation basically does is it trains a model to copy the ensemble. And specifically, oh, sorry, not description. Specifically, it tries to match the distribution over that the ensemble predicts. So what we basically want the model, to make kind of the same predictions or the same correct predictions, the same mistakes as the ensemble. So the idea is we have this big ensemble, which is called the teacher. And then we have a smaller model over here called the student. And based on some data, we make a prediction of a probability distribution from the teacher. And then when we optimize the student, we use the cross entropy loss over this probability distribution in the student. So you can either do this directly on the training data that you use to train the teacher. You can also alternatively do this on completely unlabeled data and just use a whole bunch of data to train the student based on the predictions of the teacher, even if you don't know if they're correct or not. So, and this has been shown to increase the accuracy of the student network notably, even if you have the same like model architecture and parameters and stuff. Yeah.
Can you reduce the dimensions of the student network, like try to compress it?
So I guess kind of the whole idea is that the teacher is much bigger than the student. So usually this is something with much smaller.
No, teachers are like a bunch of models together, right?
Or it could be a bigger model. That's also an option. This paper here is specifically about sequence-based models, and actually things get a little bit tricky for sequence-based models, which is what this whole paper is about. This paper that I've cited here is wonderful in that it starts with a very clear explanation of distillation, probably more clear than the original paper on distillation. But then it goes step by step until it does something that seems like it makes no sense whatsoever, but it actually works. So basically what they do is they generate the one best output from the teacher, and then they train on that using maximum likelihood. So The idea is that you would generate output using the big network and then train your model to reproduce that output. So another method of ensembling is called stacking. This is a method that's useful if we have two very different models where the prediction of outputs is done in a very different way. So let's say we had a phrase-based translation model and a neural translation model. So the phrase-based translation model in the neural translation model. I dropped that on the slide. But basically, the idea here is a phrase-based translation model is not neural in any way. It doesn't make word-by-word predictions, so it'd be very difficult to incorporate. So what you can do is you can first take the output of one system and then use that as input to another system. So maybe a better example would be like a standard. A better example is you have a dependency parser of one type, which calculates dependencies in a graph-based dynamic program or something like that. And you would like to feed that into another dependency parser that just predicts labels word by word. So what you would do is you would take the predictions of the one dependency parser and then feed them into the network in some way as input to the network, and then you would use it to bias your choices as you walk through the sentence. Okay, so that's the end of ensembling. Are there any questions here? No. Okay. So then the next question is, how do we evaluate sequence models? The basic evaluation paradigm is you have a test set of parallel inputs and outputs. You use your system to generate outputs. I put translations because I'm an MT person and everything becomes machine translation in my mind. But they could actually be any type of output, like a dialogue system output or whatever. Then you compare the target translations with the reference, or target outputs with the reference output. So perhaps the best way to do this is human evaluation. So if the correct answer here of this translation is Taro visited Hanako, which are two Japanese names because it's a Japanese sentence, then we have outputs like the Taro visited the Hanako, or Hanako visited Taro. There's a bunch of different kind of human evaluation measures that you can use. One is adequacy. And adequacy is basically whether you can get the meaning of the sentence from the output. And with respect to this one, the first one's right, so of course it's adequate. The second one is you can tell what it's saying, even if it's strange English. And then the third one is it looks like perfect English, but it's wrong. It doesn't reflect the input. Then the second evaluation measure that people use is fluency. So you have like yes. For the first one, it's fluent English. The second one is strange English. So no, it's not fluent. Then the third one is fluent English, even if it's wrong. And then another thing that people do is often kind of a ranking-based thing. So you show two things to people and say which one is better. So these are kind of the three standard ways you evaluate these models. One notable thing is that neural models tend to be very, very fluent. They tend to generate beautiful English that looks, completely correct, especially well-trained models. But they tend not to be adequate. So they tend to lie to you and basically say, give you this beautiful-looking sentence that isn't actually correct or doesn't actually match with the input. So I guess human evaluation, if you're building a human-facing system, this will generally be your final goal. But it's also slow. It takes time for people to do, expensive, and sometimes inconsistent if you ask people to do things. So instead of this, there's lots of measures. BLUE is a famous one that probably a lot of people have heard of. BLUE score, basically what it does is it looks at how many n-grams match between the reference and the system. And this works by comparing n-gram overlap and also how long the output is, et cetera. The pros is that this is easy to use. It's also good for measuring improvement between very similar systems. The cons is often that it doesn't match with human evaluation completely. It's also bad for comparing very different systems. So if you come up with a system that's just a completely radical departure from anything anybody's ever done before, and you evaluate it by blue, you may be kind of deceived. So one example of this is right at the beginning of neural machine translation. Neural machine translation wasn't actually better than phrase-based or standard machine translation methods, but the blue score was a lot better because it generated very fluent output. Now neural machine translation systems are better than the previous systems, but if you're comparing very different things, sometimes you can be deceived by this. There's a bunch of methods that have been proposed to kind of fix this problem. One is Meteor. This was made here at CMU, and it's maybe the second biggest, the second most common one. And basically the way it works is it's like blue in the overall principle of comparing with a reference, but it has a whole bunch of tricks implemented in it, essentially. So it considers paraphrases. So if you get words that mean the same thing with slightly different wording, it can consider that. It does reordering, and it does like function word and content word distinctions. Yeah.
I am but in view of how does having a radically different system actually impact the evaluation, because you're essentially
Okay.
comparing the output data to.
So that's a good question. So the answer is basically that. So another thing to be aware about blue is if you generate much shorter things or much longer things than the reference, you can pay a big penalty. So let's say you have one system that's just really good at getting the length correct, and another system that's not very good at getting the length correct. The system that's not very good at getting the length correct will automatically be hugely penalized. Another example is neural MT systems. They tend to get strings of function words correct very well, like I am planning on going to the store, or something like that. Where the actual answer was, I am planning on going to school. So the store is wrong, but all of the other stuff is in a beautiful, grammatically correct structure. Where like a phrase-based system might get the words correct, but might get them in a strange order. And if that's the case, getting the core content is the most important thing. The neural MT system will fail at that, but it will get everything else perfect.
So you would do like in terms that the model which replicates the data most accurately.
Right, and it doesn't care about what the core content is. It's just as happy if you get a bunch of function words correct. So that's, yeah.
So just to confirm, in the case of the blue score, if the sentence that the system output was Taro went to see Hanako,
Yeah.
it would be heavily penalized even though the meaning is the same.
Yes, and Meteor is designed specifically to fix that problem because it considers paraphrases. So yeah, the pros is that this is generally significantly better for blue. So like for image captioning, I think this is now kind of the de facto standard that a lot of people use. The problem is that it requires extra resources for new languages, so it's kind of language specific, and it also has tunable parameters, so it's a bit more complicated. Yeah.
Basically, use and do like on the validation set, and use on that decide when to stop.
When training models, yeah, like the way, yeah.
Directly use the evaluation metric.
So when you want to decide when to stop your training, so this is something very important to avoid overfitting. I think I talked about this in previous classes. What you basically look at how you're doing on the development set, and if this is your loss function, you pick the model right here. If it's blue, you want to pick the model when you get the top value here. And basically the answer is yes, you want to use your final evaluation metric. The only problem is blue fluctuates a lot more than your loss function. So at the very beginning of training, you can get fooled by it fluctuating a whole lot. So there are kind of like pros and cons, but I would say that in general, stopping when blue or your final evaluation metric is the best idea.
So
Yeah.
is it possible to use blue as a training target?
Yes, it is, and I'll talk about that in another class. Yeah. In a few classes. So you can also use Perplexity. So this is the actual loss function that you're calculating. The pro about this is sorry. Yeah, maybe I didn't explain this very clearly. But one of the problems with Blue and Meteor, for example, is there's actually lots of different ways to translate something. I had a good example before, went to see and visited. And even though Meteor tries to fix this through paraphrasing, it can't do big structural paraphrases or other things like this. So one thing that people do is they prepare multiple answers. So this is especially important for something like dialogue, where there legitimately are a huge number of answers to a particular question. If you prepare a whole bunch of references, this can help improve the accuracy or correlation with human evaluation a whole lot. The only problem with this is that it takes a huge amount of time to prepare all of these references, and it's not always easy to do. So one advantage of using Perplexity is this actually naturally solves the multiple reference problem, because what you want to do is you want to assign probability to any of the feasible hypotheses that you could output. And Perplexity will be penalized if you don't give high probability to the feasible hypothesis, but it will do well if you give probability to all of the hypotheses. The con to this is that it doesn't consider decoding or actually generating output. But I guess my point here is that very often people will only look at Blue score or something, but actually Perplexity is a pretty reasonable metric, and it's probably a relatively good metric for things like dialogue, where Blue is just horrible. So it's worth looking at the Perplexity or the loss function directly if you're doing something with a lot of variance. So kind of a contrastive note here. Let's say you want to evaluate an unconditioned generative model. Let's say you want to evaluate a model where basically you want to generate Harry Potter books. And you know what a Harry Potter book looks like, but you don't say, I want a specific Harry Potter book. I just want something that looks like a Harry Potter book. So in this case, you're calculating P of X. You're not calculating P of Y given X. So one obvious way to try to evaluate this is doing human evaluation. So you could show this to, you could show the generated text to a human and say, how good is this Harry Potter book that I generated? There's one kind of problem with this evaluation paradigm. Can anybody guess what this is? Oh, so just a...
Is it too expensive? Or is it too subjective?
It's expensive and it's subjective. Those are two good reasons. But
Maybe the loss function.
so this is irrespective of the loss function. This is for evaluation of the generative. So this is kind of a problem in image generation. Like you see a lot of image generation from with GANs, for example, if you're familiar with GANs. So I have this fictional GAN called CopyGAN, which basically just randomly selects something from the training data and shows it to you, and it's pretty good, right? You know, it will generate pictures that look beautiful because of the pictures that are in your training data. And if you do human evaluation on them, of course humans are going to say, these look good. These look like real pictures. So the big problem with evaluating a generative, unconditioned generative model is you can just memorize the corpus and you'll do perfectly. So you aren't testing generalization at all. And this is actually a pretty big problem. It's very difficult to evaluate unconditioned generative models properly. Perhaps Perplexity on a held out set is about as good as you can do. Another idea that I just heard like a week or two ago, which is a pretty good idea, it was attributed to Mohit Iyer, who's at AI2 now and will be training UMass next year. But the idea is you have your training set, and then you have your test set, and then in your test set, you basically take the first 5 sentences of the Harry Potter novel, and you say, okay, I'll give you the first 5 sentences. Now you have to generate the rest. And that's it seems like a pretty good test to me, because you need to be coherent with the stuff that you've already seen. So that's about as good as anything I can think of, but evaluating these models is actually pretty difficult, and I think a few people do this properly. So any other questions? No? Okay, so finally I'm going to do a few case studies in conditional language modeling. This is just to show you what the kind of things this has been used for. So as I said, kind of the original, oh yeah, sorry, go ahead.
For the book generation, could you do something like an anti-plagiarism test robot? Like if it generates something exactly same as a previous book, then.
So that would be another option. How to define that formally is not very clear. So if you could come up with a way to define that formally in the context of generation, I think that'd be very interesting. So from the first way is from structured data. So this is an example. This is maybe one of the first examples of kind of like generation from structured data with neural networks. And basically what they did here is they had a dialogue system where you would first kind of pick what kind of response that you want to do. And based on this kind of structured data about the response that you want to do, you would generate your output. So you'd be given a whole bunch of like parameters for your output and have to generate a dialogue response. This generation from structured data is still a difficult problem. So there's a really nice paper recently called Challenges in Data to Document Generation. And basically the task here is one that I mentioned at the very beginning. You're given a basketball, a table of basketball statistics, and you have to generate a document describing this basketball game. And this is kind of cool. You have to generate a long, coherent thing. It has to accurately reflect the input. And the interesting thing here is if you look at what a standard or kind of smart attentional sequence model does, all the red things are things that the model just completely made up. So they're all things that look kind of right, but don't reflect reality. So this is the standard problem with neural models. They take the input and then they make up things that look kind of nice in the output. So I'd recommend this paper if you're interested in generation type things. Another one. This is one of my papers, but what we did here is, in addition to the regular encoder-decoder model, we added a couple kind of tags. So this is kind of combining the encoder-decoder model with the generation from structured data. So you have a few pieces of structured data. You also have a latent representation, and you can use this to do things like conjugate words, or other things you could do is change an impolite sentence into a polite sentence, or other things like this. So there's lots of applications to a thing where you can kind of control the output, and this is one example of that.
Is the latent representation an external? Could it be an external?
Yeah. So
representation learned from some other external model.
Yes, it could be. I'm actually going to talk about something similar to that also. So this one works if you have like tags, like plural, noun, past tense. And if it's a more unstructured thing, there's something I'll talk about next. Yeah, actually, exactly next on this slide. So this is another kind of interesting model. Basically what they did was they have TED Talks. So TED Talks, if you're aware of them, these are talks by a speaker about a particular topic. And they train a language model that basically goes from the description of the TED Talk to the talk itself. So you encode the title, description, keywords, author embedding, and then you do, they use various encoding methods like a bag of words, a CNN or RNN. And they also have various methods for integrating this. They either integrate it into the recurrent layer of the recurrent neural network, or they feed it directly into the softmax layer. So what this allows you to do is basically say, okay, I have a talk with this title by this person, and I'd like you to generate it. So another thing is, this is a kind of interesting paper where they generate from lists of things that you would like to have in the output. So they basically have a name of a recipe plus the ingredients of the recipe. And they propose something called a neural checklist model, which basically checks off when you've added each of the ingredients to the recipe. So the model looks kind of like this. You input pico de gallo and chopped tomatoes, onion, jalapenos, salt, and lime. And the output is something like place tomatoes in a bowl, dice the onion, and add to the tomatoes. So this is a kind of interesting task, and their model for it is kind of clever. So if you're interested in generating from like lists of things that you would like to have in the output, this would be a good model for that. Another one that I almost probably don't even need to talk about because it's so popular is image caption generation. So the idea here is that you have an image, and then you want to output text, and the image is encoded using a standard image-based a standard image encoding neural network like a CNN or something like that. One important thing here is because the data sets for this are pretty small, it's pretty standard to pre-train the image recognition engine first on a large database such as ImageNet, and then you fine-tune it or you use the representations learned to generate that. Another interesting paper that I've seen recently is a paper on generating definitions for word embeddings. So this is a model that's not an encoder-decoder model. It's a model where you just have a vector and you want to generate something from the vector. And so you get the word vector for each word, like brawler, butterfish, continually, creek, etc. And then you input this into the decoder, and then you try to generate the definition. And you can get things like brawler, a person who fights, a butterfish, a marine fish of the Atlantic coast, continually in a constant manner. We've actually looked at this data, and I can tell you that these are probably cherry-picked examples because it's not this good in reality. But it's a very interesting idea, I think.
How is this trained again?
So basically, it's a decoder where you input the word embedding. You can either input it to initialize the decoder, or you can input it at every time step.
No, I mean like the data and
So you have a dictionary where the dictionary has words with that.
So if I give a new word, a test word, it's gonna like find that.
Yes. Yeah, it's pretty interesting. And as I said, it kind of works for some things, but it also kind of doesn't work for some other things.
How big is this dictionary?
That's a good question. I don't remember. It's maybe 40. Do you remember? No. It's maybe like 40,000 or 100,000 or something like that. Yeah.
In the case of such tasks, especially if it's a novel task, how does one usually set up baselines?
So I think that's a good question. So if it's a novel task, how do you set up a baseline? I think you just do the thing that seems kind of obvious first. So in this case, the kind of obvious thing is to initialize the hidden state of the decoder and then generate an output from that. Because it's very similar to what you would do in the encoder-decoder architecture. And then in addition to that, you find out where that's making mistakes, and then you make improvements on top of that. And, fortunately for a new task, your baseline can be something relatively simple. So kind of in a research project like that, then the proposal of a new and interesting task kind of becomes the main contribution, and then you do a few small improvements on top of that. Yeah, so the baseline is the standard sequence model, and they also added additional information about the affixes and hypernyms. So the affixes are like ER, for example, and the hypernyms are like brawler. It would be like a type of person or something like that. So by adding this, they were able to find improvements. So yeah, that's all for today. I'll be happy
I have a question on
Yeah.
evaluation. So if I'm let's say for summarization, if I'm summarizing a very large document, and I just want to give relevant facts, and I basically want to evaluate if all the relevant facts are actually covered, and I'm okay with a lot of data in unnecessary data being used. So what is the best way to evaluate it?
So what is the best way to evaluate something like summarization? So actually there is, for summarization, it's standard to use Rouge.
What is different in evaluating?
So Rouge is an evaluation metric for summarization, and it focuses on recall of the words in a gold standard summary. And that's precisely because you want it to reflect the relevant facts in the summary. And so recall is a good way to do that.
Let's say I'm generating something as an let's say a user keeps filling in certain types of data, as in generate certain types of data, and I'm having a model just replicate them. I'm trying to get an example. Maybe reviews, like a user is generally giving certain types of reviews to actually generate similar reviews. But my review would the generated review would basically just focus on relevant content about the product. But when a user is inputting it, there's a lot of extra content, like I went to the store and I did this and that, and which the model wouldn't generate. But in case of Rouge, wouldn't a model also use, would it be actually able to handle such cases?
Well, so this is kind of task specific, so maybe we can talk about it afterwards. But basically, the Rouge, you would create a gold standard summary, which should reflect those things. So I think it works. But it's no evaluation measure is perfect. Anything else? Okay. If not, I'll finish up. Thanks.